Hello, this is Miraj Patel, and today we're going to be starting Unit 10 and ending it also at the same time because it's a pretty short unit. And so Unit 10 is all about reaction rates and temperature relating to reaction rates. And so, first part we're going to be talking about is temperature in chemical reactions, and then the second PowerPoint is going to be about reaction rates and how they can change in collision theory. And so, without further ado, we're going to start talking about heat and how it relates to reactions. And so, here we have the definition of heat. And so, heat is energy transferred between objects due to a difference in temperature. And so, although most people think of heat as, uh, you know, um, stuff that's very hot, like, the hot temperature outside, heat is energy transferred. So this is not like high temperatures or anything like we think about in everyday. It's energy transferred between objects due to difference in temperature. So just let you know, and it's important that uh, we know that it moves from warmer to cooler objects. So heat only flows from hot to cold. It never flows cold to hot. So when people say don't like when you leave the refrigerator open and people say that don't let all the cold air out, that's wrong in with the definition because heat flows from hot to cold. So it doesn't make sense of cold flowing out. So pretty much when you leave the refrigerator open, you're letting the heat in. So a more correct definition or statement would be don't let the heat in instead of saying don't let the cold air out. So remember, heat flows from hot to cold. And so if we have these two objects, this hotter object because the thermometer is higher, the heat will move to this object here because it's cooler. And so now we're going to talk about the law of conservation of energy. And it's just like the law of conservation of mass, but with energy. So in all chemical or physical processes, energy is neither created nor destroyed, but it can go somewhere, so it can move. So energy changes always involve a system and surroundings. So the heat never just disappears. It either just moves from what we're looking at to the environment around it. So a system is just what we're focusing on or the reaction in chemistry. And then surroundings is everything else around it. So if heat's not in this, it must be in the surroundings. So always remember that. So heat never just disappears, it just moves to the surroundings. And so here we're going to talk about the two different types of reactions. We have exothermic and endothermic. So exo, if you know your prefixes, exo means outside. So just think about like extraneous or outside information. So exothermic and thermic obviously means temperature. And so if you think about exothermic, exothermic is heat moving outwards. So just like in this diagram, uh, the system releases heat to surroundings. So think about exo and thermic. So the temperature moves outside. And then endothermic is the exact opposite. So endo means inside, so and thermic is temperature. So endothermic would mean that temperature moves in or heat moves in. And so it means system absorbs heat from surroundings. So notice how we have the system and heat moves in, and exothermic is the exact opposite, heat moves out. And it's important to know that endothermic reactions feel hot because the heat is released to the outside. And then endothermic is exact opposite. It feels cooler because the heat is being absorbed. So it takes away heat and makes it cooler. And hence the thermometers. Here it's at 20 degrees and here it's at 60 because heat's being released and heat's being pulled in. And then we're going to talk about several charts with potential energy of bonds. And so here we have a chart, and this is the potential energy of the system or of the bonds. And so we have potential energy here, And then we put in energy here, and we break these bonds, just like this. And notice as we put in energy, energy from the outside is released. Is absorbed. So notice how the blue energy bar went down because we put in energy into this system. And then energy is released as bonds are formed. And so this green bar goes back down. And notice how when uh, the energy is used up, this green bar, the blue bar goes up. And so we can do the same graph but draw a line, and this is the same exact graph, but this time it puts the blue energy or the light and heat energy out that's in the surroundings on top of it. And notice how the energy is always the same, but just the location has changed. So here we have medium amount of energy in the chemicals. Then we put in energy and the surrounding energy goes down, hence the blue bar, short blue bar. And then as the reaction happens, so here's the reaction happening, energy is released from these chemicals, and we have a lot of energy in the outside. And so because energy here and here, we compare these two and we can figure out if it's exothermic and endothermic, and we'll talk about that in a second. And so here we have a potential energy diagram. So just like the green bar, this represents like the green bar in chemical reaction. So here we have reactants, which is always starts on the left, and products are always on the right of the graphs. And so reactants, they have lower energy than the products. And so if energy is lower, it must have taken in energy or absorbed energy to get more energy. So energy must have been absorbed to gain energy. And so if energy is absorbed, just like in endothermic and exothermic reactions, it's always in heat. So if it absorbs energy, it must be endothermic because heat went inside the system, and that's how we got more energy. So if it absorbed energy, or if the products have more energy than the reactants, it gained energy. So it's an endothermic reaction. And because it's endothermic, so it gained heat, think about it. So if the system gained heat, that means everything around the system feels cold. So it feels cooler. So this would be like if we had ice form. So because the water, if we have ice melting, so or some reaction where we need to take in heat or we need more energy. And so here's another graph of the same exact thing, but we have this little hill in the middle, and this little hill is called activation energy, or E to the subscript A. And activation energy just represents the energy we need to start the reaction. So here we have the energy of the reactants at the very bottom and energy of the products. And notice how we gained energy. So that's how we have delta H, which is the change in energy. And so we definitely absorbed energy because we have more energy in products and reactants. So this is again endothermic. But this little hill in the middle represents activation energy, or energy to start a reaction. So pretty much just think of it as pushing a ball up a hill. So before we get the ball rolling, like here, we have to push it up and put in energy and get to the top, and then it can fall down and react. So just like that, we have to put in energy in chemical reactions. And now we're going to talk about exothermic reactions. So here it's exact opposite. So reactants have more energy than the products. And so energy, if it's not in the system, it must have been released to the surroundings. And so we have less energy in the system. So energy is released into the system because we have less energy in these chemicals or in the system. So the outside gets more energy, so it gets hotter, and it's exothermic again because energy is released. And again, outside feels warmer because energy was given off to the surrounding. So this would be just like fire. So you know, we have wood, and so wood has a lot of energy, and so once we burn it, the flame, we have to heat up the wood, so that would represent this activation energy. So we have to put in some heat, and then once the reaction happens, um, we end up with ash at the very end and smoke. And so ash and smoke, because they don't have much energy, we can't burn it just like wood. So wood definitely has more energy than the ash, and so this would be an example of exothermic. And like I said, exothermic reactions do feel hot, and so definitely fires are hot because we burn, we release this energy, and we get less energy, and so the energy goes into the surroundings. And again, this little hill here represents activation energy, and it's important to know activation energy is always measured from the reactants to the top of the hill. So it's always reactants to top, and then difference, or delta H, or difference in energy, to tell whether it's exothermic or endothermic, is measured from reactants to products. So if products are lower, energy was lost, so it's exothermic, like fires. Think of actually cold packs. So when the when cold packs react, they take in energy, and so that's what makes your hand feel cold. So that's what endothermic reactions are. And then exothermics are opposite, just like this one. The reactants have more energy than products, so they release energy. And so here we're gonna have two scenarios. So describe the direction of heat flow as water melts. So where does the heat flow? So when we have ice, ice is cold, and so we heat it up to melt. So where would ice get heat from? And we talked about two places, the system. So in this case, the system would be the ice, and then the surroundings would be the air. So when ice melts, it gains heat. So heat has to come from the surroundings, so from this air, and it goes into the water to melt it. So if heat goes in, what example would this be of a reaction? Would it be endothermic or exothermic? So if heat flows in, it would definitely be endothermic. So think of endo as like uh, think about endo as like entering. So endo entering. So heat entered. And then here we have during freezing weather, farmers protect citrus crops by spraying them with water. And honestly, I was surprised when I learned about this. And so it all makes sense. Uh, so we spray water onto these oranges, and once the water freezes, so if water freezes, we know that to freeze water, we have to cool the water down. So if the water loses heat, where would the heat go? So the heat in the water goes to the surroundings, and so that's actually why farmers spray crops with water so it freezes, so because the water loses heat, and so this heat heats up the oranges, and that's why they do this. And so again, so as the water cools, because water needs to get colder to freeze, it releases a lot of heat to the oranges, and that's what keeps the oranges warm, even though they're covered in ice. And here's a quick quiz to see what you learned. So, the energy released when a piece of wood is burned has been stored in the wood as sunlight energy, B, heat energy, C, calories, or D, chemical potential energy. So, remember how I talked about how wood has a lot of energy, and once we burn it, it releases heat. But once it's stored, just like a normal piece of wood, it's technically chemical potential energy, because you can think about it as potential energy is energy not used, it's just stored, and it's chemical because wood is a substance, so it's stored as the wood. And I know this question might not be related, but I'm sure most of you got this just from general science in middle school. So potential energy, again, is just like energy that's sitting there as a potential to do something. Like, Sort of like gravity, how like if we have a rock on top of a hill, it has a potential to fall. Or if you have like batteries, because if they're not in use, there's no energy used, so but it has a potential of generating electricity. So potential just means that it can be used. And so, which of the following statements about heat is false? A. Heat is a measure of temperature. B. Heat always flows from warm objects to cooler objects. C. Adding heat can increase the amount of energy in an object. Or D. Heat flows because of a difference in temperature. So, if you think about it, let's think about the ones that are true. B. Heat is always flows from warmer objects to cooler objects. That is definitely true, like I talked about. Remember, when people say don't let the cold out, that's actually false because it's actually heat moving in, warming up the freezer or refrigerator. So we know that heat flows from warmer to cooler objects. And then C, adding heat can increase the amount of energy in objects. That's definitely true because if we add heat, heat is just like kinetic energy, and so if we have more kinetic energy, it increases energy. And also D is true because heat does flow because of difference in temperature. So if you have a difference, that means energy will flow to balance it out. So B, C, and D are true. And so A is definitely false because heat is just a change, or let's just go back to the definition so you know what the exact correct definition. So heat is more like a transfer of temperature, the difference. And so here's the exact definition. Heat is energy transferred between objects due to difference in temperature. So this is actually the energy transferred, not just a measure of the temperature. And by the way, it's measured in joules. And so now we have question 3 here. So fill in the blanks. So in a endothermic reaction or an endothermic process, the system blanks heat when heat is blanked its surroundings. So surroundings blank. So let's just fill in the blanks by defining endothermic processes. So endothermic means that heat is put into a system. So think about endo as entering, and then thermic is temperature. So heat enters. So the system definitely gains heat instead of loses because gains heat is entering heat. So it has to be A or C because those are the only two with gain as the first blank. And the second blank is the same. So the system gains heat when heat is absorbed from, and so it doesn't matter. So we have to look at the last blank to like find out which one's correct. And so heat is absorbed from its surroundings, so the surroundings blank. So if we take in heat, so if we take in something hot, the surroundings will cool down. So the system gains heat, and when heat is absorbed from its surroundings, so the surroundings will cool down. Because when we take in heat or energy, the particles around become less energized, so they become cooler. So the correct answer is A, and we just figured it out by thinking about endo, so coming in, so heat must move in or gains heat, and it's absorbed from surroundings because, and then it cools down the outside because if heat moves in, energy moves in, so the outside must lose energy. And so here we have one more PowerPoint to wrap up Unit 10. And so this is going to be all about rates and reactions. So we're going to be talking about reaction rates, collision theory, and 5 factors affecting rates. So here first, before we start, we're going to be talking about rates. And so a rate is a measure of change over time. And so just how speed is a rate, because speed tells us, or speed tells us how fast or they change in a given amount of time. So we can have people moving 10 meters 1 second or 50 meters 1 second. So like those tell us how fast something's going on. And same thing we have in reactions. And so here we have reaction rates. And reaction rates are rates at which reactants change into products over time. So just like how those sprinters have rates or speeds, how fast they're going to finish it, we have reactions which tell us how much time it'll take for all the reactions to change into products. And it pretty much tells how fast the reaction is going to happen or get consumed, and reactants to get consumed and turn into products which get formed. And so here, for example, we have two different reactions. We have TNT and rusting, and we know that totally that TNT happens at such a fast rate, it's almost instantaneous, like that. And then rusting is like a worm crawling, like it's so slow. It takes years and years for things to rust. But notice how the one happens faster and then the other one happens so much slower. So this all has to do with reaction rates and how fast they're going. And so again, rates tell us how fast the reactants will change into products, and over time, just like in this little demo here, as we move in time, so it moved only like a few seconds, there will be more and more products for the blue dots. And notice how at the very end, or half a minute, or whatever hour, there's so many more blue dots than reactants. And so notice how it changed. And so rates tell us how fast this will happen. And so now we're going to talk about collision theory. And collision theory all has to do with reactions and how particles collide. So here we have two types of collision. We have ineffective, so it's not well. So for example, we have these two atoms. So let's just think about this as O2 and H2. O2 and 2H2. And so they hit, but they all bounce off because they don't hit in the right spot and form water. But if we have an effective collision, so a good collision, they hit just right, just like this, and they form two water molecules. So this all has to do with collisions. And so collision theory states that for a reaction to occur, we have to have a collision, definitely. We have to have a collision to have them touch. And then we have to have a right collision, so we have to have the right spot, and we have to have enough energy. So, for example, if you think about a car crash, so in order for a accident to happen, we have to have them to collide, but we have to have like the right spot to have like a big collision. So think about a car crash. So if one car hits the other car while they're going the same exact way, it won't make a good collision. But if we have them hit with like proper orientation, like front to front, and if they hit hard enough, we can have the perfect collision. That sounds like a violent example, but that's sort of true. So same thing with molecules. So we have to have a collision with the proper orientation, so they have to touch in the right spot, and they have to have enough energy. So we can't just have a collision when cars are moving 2 miles per hour. That wouldn't work. But if we have a collision at when they're moving 50 miles per hour, that will make a great collision. So sorry for the violent example here, but that really demonstrates how collisions work. So we have to have the right orientation with the right amount of energy. But also remember that they have to collide in the first place to happen. And the energy, by the way, is called activation energy. So we need enough energy to activate the reaction. And so we'll look at curves and see what activation energy is. And so here we talked about how reactions, the difference between reactants and products tells us if it gained or lose energy. So in this one, the reactants have definitely more energy because at a higher level than the products. So it must have released energy to the surroundings, because if it's not in the system, it must be in the surrounding. So this must be endo or exothermic. And it's exothermic because reactants gave energy away to the surroundings, so there's less energy. And this is called, and that will, and this is the same exact graph, but this time we include the activation energy, or the energy we need to start the reaction. And so this one is, so instead of drawing a line straight from reactants to products, we have this little curve which represents the energy we need to start it. And this is called activation energy, or the energy, um, this is called activation energy, and we'll look on the next slide, or the energy we need to start up the reaction to actually have enough energy to collide. So this is the temperature, or temperature when the particles have enough energy to hit and actually collide right. And then before this, the reaction can't happen. And then this, as always, the measure between the difference between reactants and products is always, it always tells you whether it's endothermic or exothermic. And again, reactants have more energy than products, so the reactants definitely gave energy away to the surroundings. So this is again exothermic. And so this is difference, or delta E, or difference in energy. And so this, and then remember, reactants to the top of the hill is activation energy, and reactants to products, the difference between their lines is delta E, or difference in energy. And remember, if it goes down, it is exothermic. If it goes up, so if products were somewhere up here, then it'll be endothermic. So always remember that. If the system loses energy and goes to the surroundings, it's exo. Gains energy, it's endo. And so now we're going to talk about the 5 factors that affect rates that the reaction can take place, and they're affected by temperature, surface area, stirring, concentration, and catalysts. So we're going to go through all 5 of these. So here we have temperature, and here's a good question that relates to this. So why does milk last longer in a fridge? And the reason is why is because of energy. So think about it. If we have a higher temperature, we have a higher rate, and the reason why we have milk goes bad faster in heat is because if we have more energy, we have more collisions. So pretty much we have more possible collisions. So it will react faster because, again, as more energy, so it hits harder, and we have simply more collisions because the particles move faster. If you remember atoms, they have, their atoms are moving so fast, and so if we have more energy, they move faster and hit harder, and they hit more frequently, because if we have tons of things moving faster, they just hit more often. And so we put milk in a refrigerator to cool it down so there's less energy, so um, they hit at a slower speed, and so they have less collision. So if we have slow things moving around, they're gonna hit less frequently than if we have very fast things moving around. So that is why we put milk and vegetables and meat all in refrigerators, so it lasts longer. And now we have surface area, and so if we increase surface area, we increase the rate, and the reason why has to do all with how much space we have to hit. And so here we have a coal factory, and notice how the coal factory burns super quickly. So look how large these flames are. And the reason why is coal factories have a lot of coal dust everywhere, all inside. And so when it catches on fire, this reaction happens so fast because of all the surface area. And we'll talk more about this right now. So let's just say we have these 2 cubes, and this cube has 4 by 4 spots. We have 16 spots on this side. But if we split it up into, like, if we cut this up, we will increase the surface area, because if we cut this in half, we would include the whole insides, so we have more space to hit. So pretty much, if we have smaller and smaller pieces, we have more surface area, because it includes more spots on this huge cube. So let's just say we cut this in half. Now we could include the two inner spots. So imagine we cut this in half and we're looking at the two halves. We just created two new edges for the reactants to hit. So if we increase surface area, we have more collisions or more spaces we can hit. So, and if we have more collisions, we are more likely to react. So that's why surface area increases rate. And stirring increases rate because if we stir something, we move around the particles, and if we move around the particles, they collide more often. And if they collide more often, collision theory states that if there's more collisions, that means it's gonna react more. And here, concentration also increases rate because think about concentration. So concentration is how densely packed there are. So like if you think about, molarity, so here we have a lower concentration than this one. So notice how many more dots we have. So if we have more dots, like this one, we are more likely to hit something in when we have more and more people or more and more dots. So just think about a squirrel on a street. And so if there's a very crowded street or rush hour, the squirrel is more likely to hit a car than if it was just like middle of midnight or middle of the night because there's barely any cars. So same thing, if we have simply more particles in the solution or in the air, they're more likely to hit, and so there's more collisions and more reaction going on. And so this picture shows the same exact thing. So here we have simple air, non-pressurized, but here we have pressurized air. So we have this bottle and we packed a ton of air in this. So notice how there's a more greater flame in this bottle because there's a lot of air in this. So if there's more concentration, the flame is more likely to react with this oxygen, and so it increases the flame size. And here, the air is less packed, so it doesn't react as much. And then we have the last one, which is about catalysts. So a catalyst is simply something that speeds up a reaction without being used. So important, catalysts are not used in reactions. Just know that. So catalysts don't react. So we can keep using a catalyst over and over and over again, and it won't be used up. So remember that. Catalysts aren't used up. And catalysts lower activation energy, or remember on that graph, it lowers the amount of energy we need to put in. So just think of catalysts as those people at fights that egg on the fight. So they're like the eggers. So they're like fight, 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 but they don't actually participate in the fight. They just help the fight happen. So not telling you to be a catalyst for fights, but this is what catalysts sort of do. They just uh, speed up the reaction or the fight, but they don't participate in the fight. So exactly the same thing. So just think about them as those eggers, those people that egg on a fight. And so here's a graph, and notice how we have reactants and products, and this hill is activation energy, or the energy we need to put in before the reaction starts. And so notice how with the catalyst, look how low the activation energy is. Compared to putting this much energy, we only have to put this little amount of energy. So with catalysts, the activation energy is much lower, so the reaction can happen at such a lower temperature. And this is exactly what your body has. Your body has these things called enzymes. I'm sure if you take in biology, you should know these, that enzymes are biological catalysts, and they pretty much just lower the energy so we don't have to reach high temperatures. So important to know, relate this to biology. So chemistry is everywhere. There's a specific field called biochemistry, which is all about catalysts in your body, so enzymes. And so remember to know catalysts just lower activation energy or the temperature we need to start the reaction. So we can start it at much lower temperature than if we didn't have a catalyst. And so again, notice the difference in energy. And so um, here we have a chemical reaction. So we have hydrogen peroxide, and we break it up into water and oxygen. And the catalyst for H2O2 to break down is this metal called magnesium oxide, or yeah, no, manganese oxide. Sorry about that, manganese oxide. And so if you do this demo in lab, I mean in your classroom, and you'll see that the hydrogen peroxide immediately starts to bubble so fast. And the gas that bubbles is the O2, and then it also forms water. And so this is manganese oxide is a catalyst because it speeds up the reaction. And normally this reaction happens so slowly because light actually breaks down this chemical, hydrogen peroxide. So that's why it's stored in plastic bottles, because light is a catalyst. But this is another catalyst that makes it go even faster. And so that is why it's stored in plastic bottles, so it keeps away the energy, so it reacts at slower rate. And so here's a quick quiz to see what you learned. An increase in which of the following will not increase reaction rate? So which will not increase it? Temperature, concentration of the reactants, total mass of reactants, or surface area of reactants? So let's just go through and eliminate answers that we know that increase reaction rates. So temperature, we know increases reactions because we talked about how we have fridges, and fridges lower reaction rates because they cool down, so there's less energy, so they hit less often. Concentration definitely increases reaction rates if we increase it, because it's simply if we have more reactants, they're more likely to hit, and they form more collisions, and so they react more. Surface area definitely increases reactions because think about it, if we have smaller pieces where they have more surface area, and if they have more surface area, they're more likely to hit, so there's more surface to hit. So just think about it, is it easier to hit a small target or a large target? Same thing with surface area. If we have more surface area or smaller pieces, there's more room for the reactants to hit, so there's more collisions. So the only one that necessarily doesn't increase reaction rate is the total mass, because we can have a way higher mass but the same surface area and it won't react much faster. So total mass has nothing to do with reaction rates. It all has to do with temperature, concentration, surface area, stirring, and catalyst. So remember those five. And so a catalyst speeds up a reaction by A. Lowering activation energy, B. Increasing temperature, C. Permanently changing a reaction, D. Supplying energy to a reaction. So remember, catalysts lower activation energy. So I just told you the answer. The answer is A. And it's important to know catalysts don't react, so they don't permanently change in the reaction, nor do they increase temperature or supply energy. They're just those eggers, or those people that egg on a fight. They're there, but they just uh, make it happen faster because they're just there, and they lower the activation energy. And so that is it for Unit 10. So in this unit, we talked about reactions, and we talked about how in the second PowerPoint, we talked about how reactions can change, and so reactions can be sped up by increasing temperature, which increases the number of collisions because the particles are moving faster, and then we can increase surface area, or the area we have to hit, and so if we have simply more area with smaller particles, remember, smaller particles, so they have more surface area, we have more area or more collisions, so more reaction rate. And then if we have lower activation energy from catalysts, we have less energy we need, so the reaction happens so much faster because it happens at a lower temperature. Then we have stirring because we stir it and disturb the solution. The molecules hit each other because we moved it around, and again there's more collision, so higher reaction rate. And then there's you know, a concentration. So if you have simply more particles, they're more likely to hit because there's simply just more of them. And then we have endothermic, exothermic reactions. So endothermic is gaining heat, so a system gains heat from the surrounding, so surrounding cools down. Then we have exothermic, which releases heat, and so exothermic reactions like fires release heat because the wood or reactants has much more energy than the products for ash and smoke. And so as it burns, we have to heat it up, get to that activation energy, and go down the hill, and the products have less energy. And so it's a downward slope. And then remember that activation energy is the energy we need to start. So remember, we measure from reactants to the top of the hill, that's activation energy, and change in energies from reactants to the products. So we just measure the difference. And so that is it for Unit 10, and the next unit is going to be all about states of matter. So until next time, I'll see you later, and I hope you have a good day.